So yes, welcome everybody. Thanks for being invited to speak. My name is Amy Juden. I am a director at the Environmental Protection Group, or EPG. There's my contact details if you want to get in touch. Very quickly, EPG, you probably know us from geoenvironmental consultancy and particular specialism in ground gas, and that's why I'm talking today, because I was one of the authors of NHBC NF94. But just to let you know that we also do structural waterproofing design. That probably helps in terms of our design skills when it comes to detailing membranes, as there are kind of similarities with the systems. And then we also have teams working in sustainable water management, SUDS, design primarily, and environmental monitoring, including those continuous monitoring instruments that can be really helpful for ground gas risk assessment. We're about 30 people now. We've grown quite a bit in the last few years. So just to give you a bit of an update. So in NF94, that guidance document freely available from NHBC, which hopefully really useful, it talks about ground gas protection design in the two sections of the report, stage 4 and stage 5, one focusing on detailing the system and the other one on specification of the exact products that should be used and making sure that all of the products that are used and the kind of details of the design fulfill the requirements. So overall, the gas design should be considered a specification. It's something that should be put in place by the designer, to be built to that spec, and they should be consulted if there are design changes through the process, as you would with other elements of design of construction. The design and detailing section is split into the following sub-stages, and the ones for specification of products are similar. And I'm going to be running through some of these key elements today. So overall, we're going to focus on who takes responsibility for the design, the competence of the designer, where you can find the right guidance for making sure that design's done right, and then the different elements of the gas protection system, so the structural barrier, the gas-resistant membrane, and ventilation systems as well, and then how to wrap up all of that information into the design report and including a verification plan within that as well. So first off, the responsibility for design. It might seem like a kind of simple thing in the construction process. It's usual to get a specialist designer to design something, especially something that is safety critical, such as this. However, we do see that sometimes that responsibility for the design of the gas protection system can get a bit lost in the construction process. The geoenvironmental consultants and site investigation practitioners are very good at determining the CS classification of the site, but then occasionally it skips right from that to installation of the system without consideration of how that CS classification is going to be met, and how all the different elements of the system that are required are going to work together in the specific situation for the building that you're constructing. So who should have the responsibility for that design? I think somebody with the appropriate competence to do so, and I'll get onto competence next. But importantly, for the commercial aspects of this, somebody who's employed under a contract to do that, holds the requisite PI cover for that, so that if anything does go wrong, who has responsibility for that element. And I believe that it's very important that a designer has a knowledge and appreciation of the gas regime and the fluxes of gases, the sources and the pathways that are actually occurring on that site, so that they've got a full understanding of the level of risk and the situation that that gas protection design system is being designed in order to mitigate. So in order to inform the production of NF94, we underwent a bit of an industry consultation, and via a survey was the main part of that. And the findings of the survey was that when we're looking at the design stage of this, the key elements where issues are coming are from those poorly defined responsibilities, followed by a lack of competence and a lack of training. So competence, I think, is number one important in that area. And we can try and combat that through, webinars such as this, and also training courses that are available. EPG are a training provider, so we do that as well. But also getting the people with the right skills together, talking to each other and producing these designs. In terms of understanding ground gases and ground gas risk and how that interacts with the design, we're looking at chartered professionals or people that are accredited with the Society of Brownfield Risk Assessment, specialists in land condition, suitable qualified people. They're all the same kind of competence requirements as are in the National Planning Policy Framework. And it may be that these geoenvironmental specialists have to work together with architects or structural engineers, or potentially, if there's basements involved, structural waterproofing designers, in order to complete a kind of holistic design that covers all of the requirements. So where can we get some guidance on what a good design should include? We included this matrix for all of the different stages that are covered in NF94. And it is clear here that those stages 4 and 5, the design and the specification, is where the guidance is a bit more scant than on the risk assessment and the other stages of ground gas mitigation. But there is key guidance documents out there. And NF94 itself provides quite a lot of detail on this part of the structure. So, that's your key reference document. Also, obviously, BS 8485 is a British standard, and it is a code of practice for design of gas protection systems. So that's the kind of number one go-to in this area. I'd also really encourage, especially if you're a non-specialist, to pick up Syria C801, which is designed for site managers, interested parties, clients, and developers. So it really spells out the basics of gas protection and helps you be an informed client. And to highlight that the design is not just about the point scoring system in BS 8485. It's not just we need this plus this plus this equals this many points, tick the box. It's a bit more complicated than that, and hopefully you'll get an appreciation of that through this talk. So the elements that make up the gas protection system are the structural barrier, or a slab included within development, the membrane, and any sub-slab ventilation that's required as well. So the design report makes up part of the design, as do site-specific details and drawings. And the other elements that need to be included in that are around each of these different 3 elements. Justification that if the structural barrier is getting points for gas protection design, why that's the case. Justification that the membrane that's been selected and the kind of suite of ancillary products, self-adhesive details or other parts, that all of them are suitable for the gas regime on the site, and also the method of construction that's being adopted, specifications for those specific products, and if a ventilation system's included, appropriate level of detail in terms of verification calculations. The verification plan should also form part of the design, and I'll run through that in a bit more detail later. So first off, the structural barrier. So there's different types of ground floor slabs that low-rise residential buildings commonly have. I've put them in 3 broad categories here. First off, a concrete cast in situ reinforced raft slab. And this raft goes across the full footprint of the plot and forms the actual foundation for the unit. It's very likely to score points when it comes to gas protection because the slab is cast in situ and structural, unlikely to have through cracking. If it does, you've got bigger problems than gas protection potentially. But when you're looking at whether to include points for it in the design, you do need to take account of the level of penetrations, joints, and the like that you do have going through the slab. Is it generally cast as one whole piece with very limited penetrations, or is it does it have joints or lots of penetrations going through it? And then also for low-rise housing, we have suspended beam and block floors. For the structural barrier element of this, that would not score any points or be relied upon as a barrier for ground gases entering the structure in accordance with 8485. Because it's obviously not a cast in situ integral slab, although these kind of designs do provide good inherent gas protection mitigation through that ventilated subfloor void that's included underneath the beam and block. And then we've got ground bearing slabs, and in a low rise residential setting where the buildings are small footprint and that cast in situ slab within the footprint of the building doesn't extend over, the foundations and has a potentially quite significant open perimeter crack all the way around it, it generally wouldn't provide a good integral barrier to ground gas because of that perimeter crack opening. Whereas when we come to much larger buildings, I know we're dealing with residential developments, particularly here as we're with the NHBC, but high-rise residential buildings could well have significant cast in situ suspended floor slabs in combination with pile caps like the pictures on the left here, and that is very likely to provide a very good inherent barrier for ground gas and score you some good points there and should be considered. Obviously the picture on the right there is not a residential slab, but just to highlight the difference there between different types of ground bearing slab when we're looking at very large warehouse structures with ground bearing slabs. Obviously the size of the slabs is a lot bigger, the joints are much more widely spaced, and these kind of slabs are also likely to provide very good inherent protection for ground gases. But what good is a slab if there's a big hole in it? It's really important when we're looking at the structural drawings and what points are allocated to that slab. And if we're using that as part of the gas protection system, we have an appreciation for how services are going to get into the building. We often see these kind of pinch points, which require quite a lot of attention during the design process in coming up in plant rooms, service entry, trenches, or into other parts of buildings. Now it could be that the service or plant room where this spaghetti junction comes up into is a very well passively ventilated space with large louvres or openings, or it's fully open to the outside air. Maybe that's required for cooling if it's an electrical substation area. It might not therefore be considered as part of the structure at all that needs gas protection, but that needs to be considered on a site-specific basis. If it is coming up inside, part of the insulated structure that's part of the internal space, particularly if it's in a small room where any gas that gets into it could build up to hazardous levels, more likely, and also there's a significant gas risk on this site, then you'd really want to look at avoiding these details altogether in the first place. But if they have to be there, seeing if you can space the ducts out better, cast them into the concrete slab, ideally make sure that there's space between them all for detailing around a membrane if that's included in the design. Something like this you can kind of put on a drawing, but when you come to see these details in real life, you get an appreciation of how difficult it can be to install gas, a very robust gas protection system around them. And I'm sure Neil, when he's talking about the installation process, will have a view on this as well. And sealing of ducts is really important. There's 3 different elements to consider: how that duct is cast into the concrete. If your concrete is a structural barrier, obviously that's not necessarily the case with beam and block floors. Second thing, if you've got a gas membrane, how to seal around that penetration to the gas membrane. And then the third thing is if that penetration through the slab is a duct with an open annulus, then how are we going to seal up that annulus once the water supply pipe, in this example, or potentially electrical cables are passed through those ducts during construction. And that's a really important element because that could be, you spent lots of attention on the integrity of your slab and the integrity of your gas membrane and making sure you seal up all of the pinholes. And then if there's a duct there that hasn't had the annulus sealed, you've got a whopping great big hole in the system. This is an example for a site where there was mine gas getting into occupied residential properties, and the graph on the bottom right is carbon dioxide levels measured within the inside space of the property. Over time, these buildings did have raft slabs and gas protection, I believe. So that wasn't the route. The only route for ingress here was through the water pipe ducts underneath the kitchen cabinets in each of the units. And as we were doing continuous monitoring for hazardous gas levels inside the property, really illustrated the point at which the sealing happened, really fully mitigating that gas ingress hazard. Next on to membranes. So choosing the right membrane for the development is a site-specific decision. There's not, as much as manufacturers and suppliers might tell you that their product is the best product out there, really the best product is the best product for the job. And that depends on where the membrane's being used in the development. It's more than just the gas transmission rate, how easily that sheet of plastic lets specific types of gases that you're mitigating through, but also the strength and durability, its ability to survive the construction process and to remain as a barrier for the lifetime of the building. One thing that we've highlighted in F94, and I want to highlight to you all now, is the use of aluminium foil core membranes. The aluminium foil is included in there because it makes the gas transmission rates through the membrane really, really low because it doesn't let the gases through very easily. But unfortunately, aluminium in a wet and alkaline environment, like in contact with wet concrete, will corrode. And we've pulled up aluminium foil core membranes from underneath cast in situ concrete slabs and have found them to look like the pictures included there, basically not providing the gas resistance that they were originally. So yeah, don't specify these type of membranes where they're going to be in contact with cast in situ slab. There's updated guidance in NF94 about different positions where a membrane is being used in the construction and what type of properties you really need to focus on for that location in the construction, and gives a bit of guidance around the types of membrane properties that are suitable for either membranes that are used above a slab on a beam and block floor and very quickly covered over by insulation and going to be well protected, or membranes that are going to be placed below a concrete slab and need to withstand, rebar being placed on top of them and concrete being poured on top of them, or potentially membranes that are going to be placed at depth within the ground under a building that might be subject to different stresses and strains within the ground as the ground moves slightly. And yeah, also to consider whether the membrane need protection layers in those different environments. And then when it comes to membrane detailing, this is a site-specific thing that should focus in on different parts of the structure, which might have difficult details, thresholds, changes in levels being particular areas. These should be highlighted in a site-specific design, thought about, and potentially specific either cross-section drawings or potentially isometric 3D drawings, as in the example on the right, produced to show how the gas membrane is going to be detailed around that part of the structure. Next on to ventilation. So we're talking about ventilation layers underneath slabs in buildings in order to mitigate and ventilate any gas flux from the ground before it has a chance to get through a slab or a membrane. Important part of the gas protection design, particularly where we've got ground bearing slabs for residential. Open void underneath a beam and block floor or open voids underneath any floors are the most effective. They don't provide any resistance to flow. But imagine taking that nice open space and filling it with gravel. It's quite easy to tell how that will restrict the flow of air through that area. And that needs to be taken account in the ventilation calculations as something we sometimes see as missed. It goes for geocomposites too. There's specific Darcy's law calculation that needs to be done alongside the actual cross ventilation calculations to check if the resistance to the flow from that geocomposite or gravel will stop the ventilation that's required for the design being achieved. So I already mentioned that the most effective form of ventilation is just a clear, open void space without anything blocking it. Next, if you're going to be using some kind of void form or geocomposite, those generally perform better than gravel layers. So the most effective way of doing that is providing a complete blanket across the footprint. But if you're doing a kind of combined design with gravel and strips of geocomposite or potentially pipes included within a gravel, it's important to design them in the correct way. The best way to encourage ventilation through all parts of that system are not to cross those pipes or vent streets fully from one side to the other, because otherwise that's basically forming a preferential pathway from one side to the other, and any gas that's coming up into the gravel area is not necessarily going to be ventilated by that. If we instead interleave those pipes or strips, stopping them short of the cross ventilation, as on the diagram on the left, then that will force the air to move through the gravel either side of the vents and the pipes. So if the vent strips or pipes cross right from one side to the other, then that design is only providing pressure relief through that gravel, not ventilation. Doing full ventilation calculations for these kind of more complex designs, rather than just a simple open ventilated void on low-rise houses, potentially a situation where there's single-sided ventilation or you're using geocomposites or gravel layers, require proper calculations using the gas flux for the site and showing that the correct ventilation is going to be achieved with all of the parameters that have been used in those calcs to be fully justified. And then drawings need to be provided of where air bricks should go in the building to make sure that you're not got any dead spots in the design, and that when it comes to installation, the installer and the verifier have something to cross-reference against. Wrapping up all of that information into a design report, these are all the things you need to include: justification for any points for the slab, justification for the selection of the membrane, and specific products specified. The design report should be considered a specification. It's not a list of possible options or a collection of typical details, but it does need to include ventilation calculations, as I mentioned. And then if you've got basements in the structure, integration with the structural waterproofing design, because often the same products are providing gas protection functions. Think about how you're sealing pipes and ducts, and the verification plan included in there. I've also included in here plans for borehole decommissioning if that's not already been done by the time the designer is on board. That's often a really useful thing that you can include in the verification plan as well, to make sure that someone takes responsibility for it and it's not missed. And then also on very high risk sites, thinking about if there's deep drainage on the development and how that might cause pathways from potential ground sources at depth up to the underside of the building, and allowing for that. I also say that the design report is not a detailed method statement of exactly how the installation of the system will happen. It specifies what the system is, what it needs to do, how it should perform. Installation method statements are something that the installers can provide. Here's an example of some site-specific drawings for a development, quite a complex structure that had some below-ground elements, so the integration of the structural waterproofing into those elements. On the lift pit example on the left, how the pipe penetrations are going to be sealed, and then also where the membrane is going to go. At the time you're doing the site-specific drawings, things to consider are whether the membrane needs to wrap pile caps or the like, or whether it can go over the top. and then the suite of different products that need to be used as a loose laid membrane appropriate, or does it need to be bonded where it meets with the structural waterproofing. What's included in the appendices of NHB 94 are some really useful typical details, but these are typical details. Your building is not going to look like this. These are to help, but not a substitute for actually transcribing the gas protection system onto the site-specific detail that you have. And finally, a little note about, before I get onto verification of the timber frame construction, there can be some problems with timber frame construction and how the gas protection system interacts with preventing moisture and damp in the wall cavity, sealing the gas membrane across the wall cavity if you don't have a well-sealed cavity tray has a potential for causing build-up of moisture and damp, and that's something the designer should be aware of and make sure they're mitigating. But also sealing the sole plate of the timber frame construction through the gas membrane and therefore causing holes in it. Quite simple to prevent that second one, moving the sole plate fixing above the membrane potentially rather than sealing through it. If you do have to seal through it, make sure that there's, sufficient self-adhesive around those fixings and that they're shot fired through rather than drilled through in order so that they don't cause significant puncturing. Also ventilating the wall cavity so that gas doesn't build up in there as well as moisture. And thinking about if you can utilize that airtight breather membrane around the structure as part of the gas protection system, although I understand verification of that might be difficult in order to prevent needing to seal the gas membrane across the cavity at all. So the verification plan included in the end of the gas protection design report, we think best written by the designer, as they are the ones that really know the design, understand the key risk areas, and know which bits need to be verified. The verification plan should be specific. It needs to include all elements that are being relied on as part of the gas protection design. If that's a structural barrier, what kind of QA is required on the slab construction to ensure that it's meeting the requirements in the design. Membrane verification is something I think we're all quite familiar with, the guidance in Series C735 on that. But then also verifying the ventilation system. That could be as simple as a visual check, but it is important to make sure all bits of that ventilation system match up to each other in order to provide that ventilation. So it does need to be verified, and it shouldn't just be ignored. And it's also useful to include hold points in the verification plan where the end client or developer has responsibility for making sure the construction doesn't move on until the correct checks have been made. So this verification plan should specify what needs to be verified, how it's going to be verified, who's responsible for that, and the evidence that will be provided. Some take-home points, although I'm slightly over time. My first take-home point is actually not something I was presenting on, but something Alex was in terms of getting the risk assessment right. But I think it's the most important thing. I've gone through a lot of, appointing appropriate people, getting responsibility for the design and paying for a design and all of the different elements that need to make that up, and that it needs to be site specific. I do think it's really important that we get this right because it's a safety critical item. But if we're only putting gas protection in where it's absolutely necessary, then that solves half the battle. We see an awful lot of gas protection systems getting tripped up by this kind of detailing in the design, but were they even required in the first place from the risk? If we get rid of those over conservative precautionary gas protection systems, then we can focus our efforts and make sure we do the ones that are needed right. So some other points that I mentioned through my presentation: ensuring the design is competent, understanding it's more than just adding up points in BS 8485, understanding different structural barriers that provide good gas mitigation and those that don't, sealing penetrations to the slab, to the membrane and the annulus, not using aluminium foil membranes with cast in situ concrete. Geocomposites and gravel layers restrict airflow, and that must be considered in vent calculations. Making sure that the drawings are site specific and to the development that's being undertaken, and including that verification in the plan in the design report, specifying what's to be done, by whom, and the evidence to be provided. That's all I've got. We're going to have a little break now, I believe, and questions after all of the speakers have presented. But if there's anything you don't want to raise in a public forum or you'd like to take up with us, do feel free to get in touch.